we are interested in polycrystalline materials. Some examples, as you know, metals, ceramics, and we are interested in fundamental question of understanding and control of microstructure, which is basically an ensemble of grains or crystallites that are separated by interfaces or grain boundaries, and many material properties are influenced by the type of grains that are present in microstructure and the way they are connected to each other. For example, here we do see fracture follows the grain boundary. This is a graphical kind of overview of our work and my presentation. So we work with experimental material scientists who does experiments in thin films, Katayun Barmar. And our goal, we try to understand and develop better models for starting with individual grain dynamics, and then try to understand how individual grain dynamics affects network properties of microstructure, statistical properties of microstructure during grain growth, and also our goal is to derive evolution equations for distribution functions that can serve as robust descriptors of microstructure during grain growth, and the hope that we can connect microstructural property to material properties and develop a more predictive theory of grain growth. So here is an example of alumni thin film, and here are the results that show that, for example, electrical resistivity in copper decreases with a grain size. So for example, if we want to reduce power consumption, maybe we want to develop materials that on microstructural level have larger grains. Of course, different applications might demand different microstructural properties. So important question of how we can change microstructural property and in turn also affect material properties. So in general, in pure materials, grain boundaries are non-equilibrium defects that carry excess of positive energy. So when you anneal material, for example, to higher temperature, microstructure starts to coarsen. And here is numerical simulations of that. So what we observe, that the smaller grains disappear, the average size of grains increases with time, and the total number of cells decreases with time. So the system coarsens. And here we have actually very recent in situ experiments. It's a test run of in situ experiments that are quite impressive, and only due to technological progress, only recently something like that was possible to track actually time evolution of microstructure in thin film in real time. And we do hope that we can use in situ experiments to more closely compare our mathematical computational models and develop more physically accurate models of grain growth. So that leads us to the question, so because it's a multi-scale, multi-physics process, on what features we want to focus during grain growth. So there are different questions we can ask. For example, we can look at geometric features of this microstructure during grain growth, how geometric features evolve with time. And here, it's a good time to recall some well-known facts. For example, von Neumann-Mullin's n-6 rule, which in 2 dimensions basically tells you that the rate of change of area of isotropic and sided grain is proportional to n minus 6. So on average, we expect that cells or grains with size less than 6 will disappear, with size greater than 6 will grow, and with exactly number of sites equal to 6 shouldn't really change. There is also generalizations of that rule to higher dimensions by McPherson and Schrolowitz, and it was, I think, published in Nature in 2007. We can also look at different important statistical metrics of grain growth. For example, it is important for material properties to, for example, understand the distribution of grains with a given number of sites. And here, our simulations and experiments are actually in good agreement. They're doing pretty good here. The other important metric is a grain size distribution. For example, we know electrical resistivity depends on a grain size. Unfortunately, here, our numerical simulations and experiments are not doing as well. So the disagreement in the range of very small and very large grains. From what we tried, we think it's, so what affects that, we believe is how we model these disappearance events, or we call them critical events, topological events, when grains disappear, but not only grains disappear during grain growth, but there are also rearrangements of sites, a splitting of unstable junction, and I think we need more accurate, more physically sound models that capture these topological events more accurately, so we have a better agreement in, with respect to this statistical metric, and we hope that exactly in situ experiments hopefully will give us more insights in how to model more accurately these topological events. And that exactly brings us to the question, how do we model this grain growth mathematically, numerically, and so we can test our models against experiments and also use these models to design new physical experiments as well and get new insights into physical multiscale aspects of grain growth. So I'm going to present a simplified, in many ways, model, and in some ways a toy model, but that provides important insights into the system and also helps to develop important descriptors that actually are easy to measure, relatively easy to measure experimentally and get more insights into physical systems. So I will start by presenting first a two-dimensional model, which is in some aspects closer to experimental data that we have in thin films. And what we see here is polycrystalline samples. So with two-dimensional cells that represents grains. Here is a zoom view on three grain boundaries that meet at what we call a triple junction. So in our model for now, we assume that only triple junctions are energetically favorable. It's not a bad assumption. Of course, it does happen that more than three grain boundaries could meet, but it's a more rare event. So here, each curve represents a grain boundary, which is defined by a normal vector and tangent vector. We also assume so that each grain boundary carries excess of grain boundary energy density denoted by psi. So in our model, we assume that grain boundary energy density only depends on geometric features of grain boundaries, namely the normal angle and misorientation angle, which is the difference between orientations of two neighboring grains. And later, I will even simplify further. I will assume that we have only dependence on misorientation angle, delta alpha, in order to isolate certain effects. So we, press the wrong button. Okay. So we have normal velocity of a grain boundary, we have curvature. So in order for us to model grain growth, we need to prescribe local evolution law for our system. So for dynamics of grain boundaries, we assume a classical assumption, which is actually most mathematical literature is really focused, and I presented here some of the relevant work on curvature-driven growth, on modeling polycrystalline materials. Of course, the literature is extensive, but one of the classical assumptions is the curvature-driven growth, and namely evolution of the grain boundaries according to what is known in material science literature as Mullin's equation for a grain boundary. Basically, it's a nonlinear parabolic equation, and it tells you that velocity of the grain boundary is proportional to the curvature. Mu here is a relaxation time scale, mobility of grain boundaries. So it's a relaxation time scale associated with dynamics of grain boundaries themselves. And if we don't have dependence on the normal angle of grain boundary energy density, then it simplifies even further. So we have normal velocity is equal to mu psi kappa. So in addition to that, to have mathematically well-posed system, we also need to impose some boundary conditions at the triple junctions. So in our recent work, what we did, we decided to consider more general dynamic boundary conditions and also consider effect of the dynamics of triple junctions itself. And we assume a finite mobility of triple junction. So basically, the normal velocity of triple junction is proportional to the net acting on a triple junction through the mobility coefficient or relaxation time scale, which is associated with dynamics of triple junctions themselves. So in addition, in our model, we also wanted to introduce effect of dynamics of misorientations or dynamics of reorientation, and in some way, it can be viewed as incorporating possibility of grain rotation, or could be also introduced to model actually disappearance, effect of disappearance event through introducing additional dynamics of orientations or dynamics of misorientations, and we have associated time scale to that, gamma, which is related to dynamics of orientation, so dynamics of misorientation. So these are our local evolution laws, and we can define the total grain boundary energy. And due to the way we imposed local evolution laws, we can show that the total energy decays with time. So the system is dissipative, and we have 3 different relaxation time scales, different dynamics that contribute to that dissipation. So we have dynamics of grain boundaries, dynamics of triple junctions, and dynamics of orientation. So the way I wrote here is through dynamics of orientations can be rewritten in terms of dynamics of misorientations as well. The classical, in most at least mathematical literature, so usually what you do not have this term. So the classical assumption, you assume a force balance condition, so Herring conditions at the triple junctions. So what you do, you set mobility of triple junctions to infinity, so this term disappears. And this is actually a natural boundary yes?
Are there any coupling terms in the energy? So these terms are completely independent of?
No, the local evolution was actually coupled through, for example, misorientations. Yeah. If you, okay, what happened? Okay, I don't know what happened. So yeah, if you set mobility of triple junction to infinity, so you basically eliminate effects of triple junctions itself, and these boundary conditions, when mobility of triple junction goes to infinity, becomes force balance conditions, which is natural boundary conditions for the system at equilibrium. But one boundary conditions has to be imposed if force balance conditions, which is a classical choice, or dynamic boundary conditions have to be imposed for the system away from equilibrium in order to have a well-posed mathematical model. And when we have also classical assumption, you keep orientations constant, so these terms also disappears. In our approach, we actually took a slightly different perspective, at least theoretically. Numerically, we will consider all three relaxation time scales, but theoretically, we decided let us actually relax the dynamics of grain boundaries themselves by setting mobility of grain boundaries to infinity. So what it does, your curved grain boundaries becomes as straight lines, and the entire grain growth is really defined by what happens at triple junctions and by dynamics of misorientation. So we had a few goals with that. First of all, we wanted really to isolate and understand better effects of the dynamics of misorientations and dynamics of triple junctions on grain growth. Also, once we relax dynamics of grain boundaries, the system from nonlinear coupled PDE, ODE becomes nonlinear ODE. So it's a reduced system. It's non-standard system of ODE. It's a constrained nonlinear ODE, but it's much simpler. And the other idea was that why we introduce these three different relaxation time scales and also introduce dynamics of misorientations and dynamics of triple junctions. So our perspective is that you can model and try to reproduce important features of grain growth by viewing this cellular network as a system of interacting particles. And particles here are the triple junctions and misorientations, because triple junctions basically carry information of what happens at the end of grain boundaries, and misorientations carry information about some geometric features of grain boundaries. And by modeling interactions between triple junctions and misorientations, one can actually reproduce some important properties of cellular network without directly considering like a curvature-driven growth of grain boundary as it's done in a classical approach. So once we relax dynamics of grain boundaries, so the dissipation has two terms due to dynamics of triple junctions. and dynamics of orientation. So before I will go and talk a little bit about numerical simulations, we wanted to make sure that the model we have is mathematically well posed. So in case of a single triple junction, we have a global existence and global uniqueness result for this model. For network model, so for triple junction and misorientations in a network, we have a global existence result as well. So we have some well-posedness, local and global. And once we have some confidence in our model, I will mention a little bit about numerical simulations. So we have numerical simulations that are based on full model that takes into account dynamics of grain boundaries, dynamics of triple junctions, dynamics of misorientations, and also we have simulations of reduced model. I'm not going to go into technical details of how these simulations are developed, but what I want to mention, so our grain growth simulations actually based on a sharp interface approach. So we model grain boundaries explicitly, and we model topological events explicitly, which is computationally is much more expensive, but it allows us to actually separate different relaxation timescales and try to understand better effect of different relaxation timescales when we use a sharp interface approach. So I will only mention like 3 big building blocks of simulations. The way the numerical scheme is derived, we compute a discrete total grain boundary energy. We compute, we enforce at a discrete level the dissipation of total discrete grain boundary energy, and as a result of that, we derive a discrete version of Mullin's equations in case if we take into account curvature effect. We take into account dynamics of grain boundaries. If we relax dynamics of grain boundaries, then it's basically a vertex type model, and the dynamics of grain boundaries is really defined by what happens at triple junctions. We enforce boundary conditions at triple junctions, either discrete force balance conditions or discrete dynamic boundary conditions in case of finite mobility of triple junctions. And I guess the most challenging part in sharp interface approach is handling of topological events, because, and it's not just for numerical simulations, for mathematical analysis, it's also a major challenge to analyze this system and take into account with topological critical events, because it's not just grains disappear, but short grain boundaries are being removed via splitting of unstable junction, via splitting also of sometimes appearance of double grain boundaries. So everything has to be handled in a way that enforces, in our model, we assume maximum dissipation. More details about numerical simulations can be found in one of these papers. Okay, but what I want to show, so I discussed that we have reduced model where we relax dynamics of grain boundaries. We have a full model. So what we did numerically, we wanted actually to compare in some aspects the reduced model and a full model. So numerically, I will consider the full model that takes into account dynamics of grain boundaries, dynamics of orientations, and dynamics of triple junction. And I will compare it with a reduced vertex model where we relaxed, we removed curvature effect, and we only look at the dynamics of triple junction, dynamics of triple junctions and dynamics of misorientation or orientation. And what we did, we looked at the total gain boundary energy and how it decays with time. And what we discovered, so if we set mobility of triple junction relatively low in case of full model to mobility of gain boundaries, what we discovered that the reduced model, where we have no curvature effect, and full model actually behaves similar in the sense what we see that the total energy decays exponentially fast with time. And that's consistent with theoretical results that we had for the reduced model. Theoretically, we showed for the reduced model that the total energy decays exponentially fast with time. So what it tells us that when mobility of triple junctions is relatively low, it's really the dynamics of triple junctions that define in some way the gain growth. They dominate during gain growth. And this is consistent with what was observed in some molecular dynamics simulations. And then I will talk also about recent experiments that in some ways consistent with our model and theory as well. So let me, okay, I will skip this. Let me show what happens when this is kind of a middle range. We increase mobility of a triple junction, but it's not yet in the limiting case when mobility goes to infinity and basically you recover force balance conditions. So what we start to observe in this regime, when we increase mobility of triple junction, we start to see that dynamics of gain boundaries start to play a more prominent role. And that is expressed that the total energy, so for the full model, is now decays as a power law, as 1 over t. And of course, for vertex model, reduced model, it's still an exponential decay. And in a limiting case, when you really eliminate any effect of the dynamics of triple junction by setting force balance conditions at triple junction, you observe that you have energy decay as 1 over square root of t, which is actually, to me, it's interesting that transition from exponential decay to 1 over t, and when in a limiting case, it becomes 1 over square root of t. Mathematically, it would be good to actually look how that transition happens depending on the mobility of triple junctions on this. In our model, we assume it's constant. It doesn't have to be constant. But these results are also consistent what is observed in some molecular dynamic simulations, that indeed you see the dominant effect of triple junctions during gain growth in low mobility regime, low mobility of triple junctions. And when you go to another limit of force balance conditions at triple junction, you see, of course, the dominant effect. You don't see any more effects of dynamics of triple junctions. And I want to mention a recent work, actually, and these experiments were motivated by the development of our reduced model. From my knowledge, it was for the first time observed that basically the classical assumptions, because very often in experiments when they process data, they assume these force balance conditions at triple junctions or triple lines. So here they looked at tungsten thin film, also aluminum thin film. And what they discovered, that if they make classical assumptions in algorithm when you process the data, if you assume that you have force balance conditions that you usually assume at triple junctions, when they process the experimental data, we got result that didn't make any sense. Basically, we did not observe any inverse relations between grain boundary energy and grain boundary population. So you do expect that in your system you will have much larger percentage of low grain boundary energy, much larger percent of grain boundaries with low energy, much smaller percentage of grain boundaries with higher energy, and using these thin films, when we try to extract the data and process the data under assumption of force balance conditions at triple junction, we did not observe any inverse relations between grain boundary energy and boundary population, which not directly, but indirectly indicates that, and that was for the first time, that the geometry of triple junction is actually not fully determined by force balance conditions. I don't know if it's because of maybe you have to consider other forces of at triple junctions. You maybe need to assume drag or finite mobility of triple junctions, but it's consistent with our mathematical and computational model, and our goal now is to try to check that directly to see what more direct, try to obtain more direct data of what happens at the triple junctions. Yes?
What are the different markers here on the experimental data?
Well, it's, I think, different grain boundaries, like sigma 3, sigma 11, and population. And from these, you see that there is no like inverse correlations. And similar results, so this is tungsten, and similar results we discovered from aluminum as deposited sample and also after they annealed. So that was very interesting. For a long time, actually, we couldn't make sense because we tried to, the goal was to extract grain boundary energy density. And when something wasn't going right, and at the end, we eliminated everything and we figured out that it's the assumption of force balance conditions in algorithm that process the data that makes the results that contradicts of what we expect to see. And that brings us to a relevant question. So I showed how the total energy decays with time. But no less important question is exactly to classify grain boundaries with respect to the energetic properties during grain growth or during coarsening. And for that, it's important to figure out some reliable metric. And such statistics or metric was found actually quite a long time ago, was discovered at Carnegie Mellon in both numerical simulations and experiment. So it's known as a grain boundary character distribution, or GBCD, which was found to be a stable characteristic of material. And for my modeling goals, I will introduce it in a simplified setting for now. So namely, I will assume that it's grain boundary energy density only depends on misorientation, and I can see that at this point 2D cellular network. So in that simplified settings, this GBCD is basically defined as a relative length of arc of grain boundaries that are sorted by misorientation angle alpha. So basically one can think about it as a probability of finding grain boundary with a given misorientation angle alpha. And so basically we expect, that expectation is confirmed now by simulations, experiments, and theory, that these statistics exactly will make a connection and will give us information about relation between grain boundary population and grain boundary energies.
Excuse me, where is this sigma 3, sigma 11 on this graph on the right? Where
here it's a simplified model. So yeah, in this model I don't. But on the next graph I will show which comes from experiments with the simulations. Okay, so so what was discovered in both numerical simulations and experiments that I will show in the next slide, that first of all, with statistics, with grain boundary character distribution does achieve statistical steady state. And what was also discovered that with statistical steady state, so it's inversely related to a grain boundary energy density. And in fact, at least in these ideal settings, is given by a Boltzmann distribution for a grain boundary energy density. So to us, it was a surprising result because even in these simplified settings, it's actually a very complex system, metastable, that coarsens with time, and suddenly, as a stable statistics, as a steady state, statistical steady state for GBCD, we obtain a simplest non-random distribution, which is given by a Boltzmann distribution for a grain boundary energy density. And here, experimental results here, you can see sigma 3, sigma 9, that also consistent and basically show the inverse relations, Boltzmann-like distribution between grain boundary energy and grain boundary population. So experimental results also indicate a similar relationship between grain boundary energy and grain boundary population.
Sorry,
yeah.
Can you go back to the previous slide, just before this one? The one where you have...
the other one?
Yeah, this one. Yeah, so do I understand correctly? These are inflection points, right? So this is
just to have shoulders, yeah.
But is it important this inflection point, or could they be like, say, local minima or something?
No, it doesn't. It's just here we wanted to have some like try to model shoulders. Yeah. Okay, I keep forgetting I have the pointer. Yeah, so as a mathematicians, we wanted to understand how this grain boundary character distribution with statistical metrics evolve with time and how it converges to such a steady state, which is described, in these simplified settings by a Boltzmann distribution. And in original work, which we did quite some time ago, we considered a simplified model. We basically used the similar idea. Let us model the grain growth using some kind of evolution of triple junctions and interactions with misorientations. And what we did, but we oversimplified at that time, we basically stretched the entire cellular network on 1D line. And we reduced the entire 2D cellular network to 1D coarsening network where grain boundary was represented by interval. Not going to go into details of that model due to lack of time, but what we were able to show using a reduced 1D model that didn't really model triple junctions because they became, the triple junctions became the endpoints of 1D intervals. But using that idea of removing again curvature effects and just focusing on what happens in some ways at triple junctions and misorientations, and using with the help of mass transport approximation, namely Wasserstein two implicit Jordan, Kindler, Otto implicit scheme, we were able to set up a minimization scheme for grain boundary character distribution. And using that idea, we were able to show that GBCD indeed evolves as a solution to this Fokker-Planck equation. And as a consequence of that, the steady state is given by a Boltzmann distribution for grain boundary energy density. So that theory was developed for the reduced 1D model where triple junctions were not exactly even triple junctions. And we decided to check because we have 1D model, coarsening model, and we have 2D large-scale simulations. We develop a theoretical model for evolution of GBCD using that 1D reduced model. We can check our prediction of the theory versus empirical GBCD that we can extract from 1D simplified model, and we can extract from 2D large-scale simulations, and we compared evolution of empirical GBCD versus evolution of Fokker-Planck equation, and actually large-scale simulation model gave even better agreement. And we think it's because in 2D large-scale simulations, we really have triple junctions, and simplified model kind of oversimplified what happens at triple junctions. But that was an encouraging result. And in our recent work, using actually, and that was original goal at least, but once we started, we found this model that I presented earlier useful in many other aspects. We decided, can't we use this model that we introduced for the dynamics of misorientation or orientation and dynamics of triple junctions to try to extend that theory for grain boundary character distribution to a system that describe grain growth in 2D cellular network more accurately. So here is this system that I presented earlier, written for a single triple junction and free grain boundaries. It's a gradient flow for triple junction and orientation. But since we're interested really in grain boundary character distribution, which is related to misorientation rather than orientation, we wanted to change our state variable from orientation to misorientation. It's not that hard to do. Again, you can show that it's a gradient flow with respect to misorientation and position of triple junction. But again, this is for single triple junction. How do you put this model, this system into network? One needs to somehow model the interaction of triple junction and interaction of misorientation to try to reproduce in some ways and mimic what happens during grain growth. So we decided, instead of trying to model correlations, let us first do a simplest possible extension of this model for a single triple junction and free grain boundaries to a system that models the network. And what we assume, we basically assume Langevin dynamics. We basically decided, let us use a Brownian motion to model the interactions between actually, there are no interactions, but model evolution of positions of triple junction and misorientation. And basically, it's in some way an ideal gas approximation. Okay, it's a very simple model, but let's see if it captures something interesting, something relevant to what we see in 2D large-scale simulations. And for these Langevin dynamics, for dynamics of triple junctions and misorientation, we derived the associated Fokker-Planck equation for the joint probability distributions of misorientations and triple junction. In addition, if we assume the fluctuation dissipation relations between the relaxation timescales responsible for dynamics of misorientations, dynamics of triple junction, we have the associated energy dissipation law for this Fokker-Planck equation. And not only it ensures that the system encodes some dissipation property, but it ensures that this solution to this Fokker-Planck equation converges to an equilibrium state. And later on, if time permits, I will show we numerically also in some way verified that fluctuation dissipation assumption. But we were interested in evolution of GBCD. So, okay, we can integrate out position of triple junction. And basically, we get a Fokker-Planck type equations for evolution of GBCD. And this Fokker-Planck type equation also can be shown does have a steady state solution, which is given here. And what is interesting that in general, it's actually not a Boltzmann distribution and not a Boltzmann distribution for the grain boundary energy density, especially because we have here non-constant coefficient. So the question we ask, can we provide some conditions under which steady state distribution actually will be a Boltzmann distribution? And okay, I guess I have a few minutes. And we did derive a sufficient condition, not necessary. And for that, I need to introduce two new points. So a weighted Fermat-Riccioli point, it's basically for the given misorientation delta alpha, it's a minimizer of this energy. And also if we mark 3 points along grain boundaries, say x1, x2, x3, we also need to introduce a point which we call a circumcenter. So it's an equidistant point from 3 points along 3 grain boundaries. And the condition that we derived, which was very interesting, which is sufficient condition to see a Boltzmann distribution, that if the weighted Fermat-Riccioli point, the circumcenter and the triple junction become the same point, if they all coincide, when the steady state probability density of misorientation, or GBCD, is indeed given by a Boltzmann distribution for the grain boundary energy density. And as a result of this condition, we derived 2 relations. So if, for example, the triple junction coincides with circumcenter, these relations should satisfy. And also the other local relation, if the triple junction, the weighted Fermat-Riccioli point and the circumcenter coincide, when we should have these relations, which basically connects the grain boundary energy and the geometry around the triple junction. So these are local relations which are consequence of our theoretical model. We wanted to see, do we see anything close to even to that in our large-scale simulations? Because our model is based on Langevin type dynamics, no correlations. So, and we decided, yeah, let's check these 2 relations using our 2D large-scale simulations with a local relation. So we cannot really check them exactly, but we can check them in probability. And we did, and surprisingly, actually, using 2D large-scale simulations, the full model with curvature, in fact, we did see that with high probability, both relations satisfy. And what it tells us, I guess, with emergence of Boltzmann distribution is some manifestation of some symmetry, because these relations tell us about some symmetry in the system. Why? We are not sure, but it's a consequence of our model, and we do observe with high probability that it's satisfied in our large-scale simulations. Here, I just want to show one experiment that we did to try to check this fluctuation dissipation principle that we assumed for our Fokker-Planck model. So as a consequence of that fluctuation dissipation principle, we should see an inverse relations between diffusion-like coefficient and time scale that is responsible for dynamics of misorientations. And actually, we do see when we test empirical GBCD that we do observe an inverse relations that does indicate into support of fluctuation dissipation assumptions that we made in our model to derive a Fokker-Planck model for misorientations and position of triple junction. That was also consistent with our theory. And I want to conclude by also mentioning we are extending our numerical simulations and hopefully at some point theory to 3D. So again, with a sharp interface, gain-growth simulations. So on the left, it was just one gain extracted from a network, the gain that eventually disappeared. Theoretically, the algorithm in 3D is very similar to what we have in 2D, but handling topological events is much more challenging in 3D. But I would like to mention a relevant work by Emmanuel Lazare, who also has sharp interface gain-growth simulations, but they're based, his simulations are based on different local evolution equations, different model. It assumes basically a generalized von Neumann-Mullins rule, but already for the volume of the gains. So it does assume, I think, there are like force balance conditions enforced at the triple lines. So here, our simulations based on more generalized model. And thank you.